Andrzej by André Kiveriga, Baptiste Pollion, and David Basile. So, without further ado, I let Andrei start his presentation. So it's the automatically pre-recorded part first.
Hello, my name is Andre, and today I will present our work about the randomized reachability analysis in UPAL, which was done in Aalborg University in Denmark. This is a joint work with two of my supervisors, Kim Larsen and Ulrich Newman. In the field of model checking, where formal verifications of systems is done, it is important to ensure that reliable and exact models of the systems are created. To do so during development, a user can run different verification queries to discover potential problems or bugs, very similarly to how unit tests are ran in the software development. The feedback received from verification allows the user to find and fix these problems iterative process with the final goal of creating a correct model and verifying some interesting properties for it. Unfortunately, the formal verification can be noticeably slowed down due to the most prominent problem in this field known as the state space explosion problem. This problem becomes more and more noticeable as the size of the system increases. And as the result, development process can be hampered. So this really creates a need, or simply put, it would be nice to have some efficient and scalable method for error detection that we could run quickly. So picture yourself in the following situation. You are sitting in the office about to finish some last changes to your model, and then you run the verification on this model and you leave for the weekend because you know the verification takes a lot of time, potentially several days. And you only come back on Monday and just to discover that you have probably done some typo in those changes or some other small silly mistake that you wish you could have fixed much faster. But unfortunately, this was not possible. So such an efficient and scalable method that we worked on in this paper would allow one to perform some fast randomized checking and quickly discover this error. In this paper, we introduced the randomized reachability analysis and implemented in the tool which was developed in collaboration between the Uppsala University in Sweden and the Aalborg University in Denmark, and is called UPAL. UPAL is a tool environment for modeling and verification of real-time systems that are modeled as networks of timed automata and extended with different data types such as integers or arrays. Our randomized reachability analysis excels at detection of different rare events such as errors in the models, and in fact can perform it up to several orders of magnitude faster than other existing model checking methods. Specifically, in some of the cases which previously took 23 hours to analyze, we can now find bugs in just 23 seconds. Moreover, we have the possibility to analyze models that was previously intractable by other existing model checking techniques. And we can also search for shorter or faster trace, which as well supports the efficient development process and helps the user to find errors quicker and simply understand the system better. One of the starting points that challenged us was the Herschel-Planck case. It is a system that consists of two satellites, Herschel and Planck. The satellites have different scientific objectives and thus the sensor and actuator configurations differ, but both satellites share the same computational architecture of a single processor. There are 32 individual tasks that are executed with the policy of fixed priority preemptive scheduling. And in addition, a combination of priority ceiling and priority inheritance protocols is used, which in essence make these priorities dynamic. The control software for this satellite was developed by the Danish company called Therma, and the very same company has also performed a so-called worst-case response time analysis, which is a traditional approach in preemptive priority-based scheduling. Simply put, this type of analysis involves estimating worst-case scenarios for both execution and blocking times of the task and comparing it to the deadline. But on the downside, such analysis is known to be over-approximate, which may lead to some pessimistic conclusions in that the task may miss its violation, which actually turned out to be the case for the Herschel-Planck, where this response time analysis showed that one of the tasks can miss its deadline, but such violation has never been observed in neither stress testing nor deployment. A prominent alternative for verification of schedulability is a so-called model-based approach, and its advantage is in that it considers more different parameters, such as, for example, offsets, release times, exact scheduling policies, and so on. And due to this model-based approach is able to provide a more exact schedulability analysis. On the right side, we can see a model of a task from the Herschel-Planck case. And this model, or to be more precise, a template of a model, is instantiated 32 times to represent the 32 tasks running on Herschel and Planck. Preemptive scheduling is encoded in these models with the help of stopwatches, which allows to track the progress of each task and stop it when the task is preempted. In UPAL, the stopwatch support is implemented through a concept of derivative over clock, where the derivative can be either 1, meaning that the clock is progressing as per usual, or 0, meaning that the clock is entirely stopped. Unfortunately, reachability in stopwatch models is undecidable, and in UPAL, existing symbolic analysis techniques for models with stopwatches is over-approximate, which means that they may provide spurious traces. Therefore, symbolic model checking cannot be used in such systems for disproving schedulability. First application of model-based approach on Herschel-Planck was done in this study in 2010, but it was done with a rather unrealistic assumption of fixed execution times for tasks. And in 2012, there was an improved analysis in the next study, which was carried out with each task given a non-deterministic execution time in the range of from best to worst case. However, a number of factors, which includes this interval-based execution times, preemption, shared resources, unfortunately make schedulability of systems like Herschel-Planck undecidable. So the solution in that paper of 2012 was to consider a combination of existing model checking techniques to obtain some guarantee on schedulability, even in the presence of undecidability. So here we have the summary for Herschel-Planck schedulability from that study. We have F here that represents the ratio between the best case and the worst case execution times. Whenever these values are the same, F is equal to 100%, and as we increase the worst case execution time, the F value decreases. So there were two model checking techniques used in that study. The first is the symbolic model checking technique that allowed to conclude schedulability for Herschel-Planck and did not find any potential deadline violations for F values from 90 to 100%. For the rest of the ranges, the verification was inconclusive due to the either state space explosion or over approximate analysis of UPAL. And the second technique used was that of statistical model checking, or SMC, where the core idea of SMC is to randomly generate simulations of the systems and verify whether they satisfy a given property. In this case, SMC was used as a remedy to generate concrete counter examples witnessing non-schedulability. So in fact, this technique, SMC, has proven to be quite efficient, and there were traces witnessing unschedulability of Herschel-Planck for F ranging from 0 and up to 71%. In this study, we have applied our randomized reachability analysis on the Herschel plank. And first of all, we managed to confirm the results of SMC. And not only that, we've done it significantly faster. So a case that previously took 23 hours for SMC to verify now takes only 23 seconds. And second, we have further breached the wall of what is known and confirmed unschedulability of Herschel plank for F values from 72 to 80%. Now we will take a look at how randomized reachability analysis actually works. It performs exploration based on random walks through the state space, and each of the random walks is limited by some maximum allowed depth that scales up dynamically up to a specified constant by the user of UPAL. The method operates on concrete semantics and therefore performs an under-approximate analysis of the state space and is thus relieved from the expensive symbolic computations, making it very quick and efficient. No states are being stored, and therefore this method is memory efficient. In all of the experiments conducted in this study, at most 30 megabytes of memory have been used even for large systems, while other symbolic techniques frequently run out of 16 gigabytes of memory. We have experimented with several randomized heuristics, and we have used adaptive delay choice mechanism in 3 of those heuristics. We also allow the search for shorter or faster trace. We now take a closer look at the heuristics. The first naive heuristics we tried, called semantic exploration or SEM, performs a choice of a meaningful delay, that is, a delay after which at least one transition is immediately enabled. And after such delay is made, a uniform choice of available transitions is made. Here we have a small example of automaton, which has an initial location, and it has a goal location that we want to reach. The transition that leads to the goal location requires clock x to be at most of value 1. In fact, there are infinitely many concrete random runs that can be generated in this model. In this particular case, the delays are chosen in the range between 0 and 1 as a meaningful delay to target transition B, and in the range between 901 and 1000 to target transition A. Due to the difference in sizes of these intervals, the probability of SEM to reach the goal location in one random walk is 1 over 100, which is not very efficient. The other heuristic we have tried is called random enable transition, and together with the following 2 heuristics, it in fact reverses the process in the sense that it chooses the target transition first and only. So random enable transition computes all eventually enabled transitions, which are the transitions that are either immediately available or will become such after a certain delay. And afterwards, a single transition is chosen uniformly at random. In fact, in the very same model, we would have the ability to generate the exactly same concrete random runs, but it is now equally likely to select one of the 2 transitions because in the algorithm, the transition is chosen before the delay. As the result, the probability for red to reach the goal location in one random walk is 1 over half. In the next model, there are no clocks, but there are 2 integer variables, I and j. The transition leading to goal requires variable j to be at least of value 7. In the initial location, we can only take the transition b, which increments variable I by 1, and as soon as I reaches 2, the transition a becomes available that resets the value of I to 0 and increments j by 1. The tricky part here is that if we miss transition a, we in fact are no longer able to take it in the same random walk. Therefore, the probability for SAM or ret to detect goal in one random walk is under 1%. We consider a heuristic called random least coverage that performs a uniform choice at random of a transition with the least coverage for descending edge. The coverage counters are reset after each random walk, which makes random walks independent in between each other. Since the transition A has always lower coverage counter, it will always be taken as soon as possible, resulting in the probability for RLC to detect goal in one random walk being 100%. And we also experiment with the random least coverage accumulative heuristics, where the coverage counters are shared between the random walks. The next question is how to select the delay for ret, RLC, and RLC accumulative heuristics. The intuitive approach is to make a uniform selection from the lower bound to the upper bound of the transition range of available delays. However, our previous study on randomized refinement checking has shown that this is not, in fact, an efficient strategy. In practice, most of the systems are usually concerned with either satisfying some minimal requirements or, as an example, checking if a deadline can be violated. Therefore, a certain delay probability distribution is preferred where, say, lower bound and upper bound values are chosen most of the time. However, any such fixed delay probability distribution will favor some systems over other ones. In this study, we use adaptive delay choice mechanism. The idea is to run a random walk with a certain fixed delay probability distribution and then change it if a random walk is unsuccessful. Concretely, we use the following sequence of delay probability distributions, where in the first 10 sequences, only lower and upper bound values can be selected, but just with different probabilities. The last sequence, number 11, allows to choose some values in between the bounds, but only in 20% of the cases. The dynamic depth of random walks works as follows. We start at some small depth, 2 to the power of 4 to be precise, and we double the amount of steps after enough of random walks have been performed to cover all of the sequences of delay probability distributions. We keep doubling the amount of steps until the maximum depth specified by the user has been reached. Finally, we have performed the experiments on the Herschel-Planck case, where in the hardest case for the SMC, where the F value equals to 71%, it took roughly 23 hours for SMC to detect a counter examples. In turn, our randomized techniques perform 3 orders of magnitude faster and detect counter examples in just under 23 seconds. Furthermore, we have been able to detect counter examples as far as up to F equals to 80%. We have also run extensive experiments for up to several weeks for F equals to 81, but we have not found any counter example which potentially indicates that Herschel-Planck might be schedulable starting from F equals 81. In our next experiment, we'll look at the average length of traces found for Herschel-Planck system and compare ret heuristic from experiments in the previous table against ret S, which is the version of ret with the shortest trace option enabled. In order for non-exhaustive exploration of ret S to terminate, we need to specify the timeout value, which is roughly based on the average time required by ret to find an error. We can see that with the given timeout, ret S shortens the length of the trace by a factor of 12 at the very minimum. The exact value of the timeout has to be decided by the user, which may not be an easy parameter to estimate in the setting of randomized and unpredictable exploration. In order to better understand how ret S behaves, we plot 10 runs on ret S on Herschel-Planck system with F equals 75. We can see that all of the 10 runs have found the trace of sub 2,000 steps in just under 10 minutes. And in average, it took just under 5 minutes to find a trace of sub 1,600 of steps. We perform more experiments on a number of other schedulability problems. The symbolic model checking techniques depicted in gray may provide potentially spurious traces due to over-approximate analysis of stopwatch models. SMC can then be used to generate concrete counterexamples. However, for some systems, SMC may not be applicable, as it does not support handshake communication between the models. In such cases, our randomized technique become the only method to obtain exact and non-spurious counterexamples. We further test how well our randomized reachability analysis would work in practice. We do so by using models developed by master thesis students at Aalborg University, which can be considered future model developers. The models have been developed for the gossiping girls problem. This problem has each girl that knows a distinct secret, and these secrets can be shared with other girls through calls. The girls are organized as a total graph and can talk with each other concurrently, but with at most 2 girls per call. In fact, it is a rather difficult combinatorial problem that, when scaled up, quickly exposes the limits of symbolic model checking. We're looking for a particular configuration of secrets known. Specifically, we divide girls into 2 clusters and look for the states where all of the secrets have been shared within each cluster, but not in between them. Such state is considerably difficult to find, and once missed, it cannot be found in the same random walk. The results have shown randomized reachability analysis to outperform symbolic methods by a significant amount, with the exception of one model where the performance is near identical. And at last, we test our randomized methods on a number of various scaled-up models. In all of the cases except one, our techniques perform up to several orders of magnitude faster and use up to 30 megabytes of memory at most. Link to the snapshot of UPAL that contains our randomized methods is now available in the paper, and it is also planned to have randomized reachability analysis available in the next official release of UPAL. Thank you for your attention.
Thank you very much, Andrei. So there should be a way for people to clap it somewhere in the reactions. I see there are some questions that you have already answered in the Q&A, which are actually interesting questions. Maybe you want to actually take them quickly, or okay, let's treat the open questions which were not answered. So there are 2 questions, one by Bob Rubens and one by Etienne André. So let's go in order. So yeah, you can probably read the questions and answer them.
Yes, let's take a look. So the trend shows that the better our tools get, the worse we can prove the schedulability to be of the satellite. Do you think we will keep finding problems with the schedulability of the satellite, or will there be some guarantee of schedulability at some point in the future? Well, of course, we hope that there will be some guarantee, and unfortunately, this class of problems is undecidable due to a number of factors. And before we maybe find a way to solve it, which is quite unlikely, of course, we try to obtain at least some guarantee in this particular case. So we all hope that this will be sort of, well, we can obtain some guarantees in the future, but whether it can be done or not depends on us. This work can be obviously parallelized. Can you have some communication between parallel runs? So it was actually one of the previous questions as well, if we have parallelized the random runs. And the answer is we have not done in this study. So we do not have any experiments and where we parallelize the random walks. we in fact run them just in sequence, but they can be quite easily parallelized. In fact, this is one of the future works that we plan to do them in parallel in UPAL. That should drastically increase the performance. And can we have some communication between the parallel runs? It is difficult, a question to answer from the top of my head. We would need to sit down and maybe look at what would make sense to pass between the runs, maybe something coverage related, so that some of the parts of the models that have been already explored a lot do not get explored this much by other random walks, for example. So I think that would be one of the possible things to share between the random walks. But of course, there are multiple options. And in fact, we have looked into a number of other techniques, including different tokenized versions or guided heuristics. But we have not, unfortunately, obtained any better results with those. So those remain open for investigation.
Thanks. There's another question from David in the chat. Do you see it or?
Yes, would it be possible to automatically decide the most suitable heuristic based on properties of the model under analysis? Would it be helpful for users not familiar with it? Yes, very good question. So we have thought about this a lot. So in fact, the problem of these kind of model checking tools is that there are a lot of different heuristics methods, but it really requires expertise before you can use them efficiently. So it would be really nice to do something like you suggest. We do not have, unfortunately, yet a good way of doing this. Perhaps some analysis can be done, but I think also the problem is that it's always very easy to construct evil examples. So it really makes the problem hard to analyze and be sure. But I think one of the ways this can be done is connected with one of the previous suggestions to run these techniques in parallel. So we can run all the heuristics in parallel, and then our execution time will be that of the fastest heuristic. So I think that could be a sort of easy getaway approach on how to solve this problem.
Thanks.
Okay. Are there any more questions in the audience? So just to tease you a little bit, Andre, I have a suggestion for the future work. Maybe you can try your methods also on the gossiping boys protocol and see if there's any difference. That'd be nice. That would be a first, I think. All right. Thank you very much for a nice presentation.
Thank you. Thank you.
Great. And I think we can move to the next one by Baptiste Pollian.
Good morning, everyone. My name is Baptiste Pollian. I'm a first-year PhD student at Fmics4, and today I will present you an ongoing work about the verification of a mathematical library of a UAV autopilot using Fmacs4. This work is a collaboration with Christophe Garion and Xavier Thirieux from Fmics4, Gauthier Entenberger from ENAC, and also Pierre Roux from Onera. The formal methods are verification techniques that are based on mathematical model. Today, they are largely accepted as complementary method, with the more traditional one like code review and the use of tests. And this is especially the case in some critical systems where some standards recommend the use of formal methods. So formal methods are divided in different domains: abstract interpretation, deductive method, or model checking. And each of these domains has several tools that implement the formal methods. A question we can ask is, even if all these tools are based on strong theoretical results, can they be applied in an industrial context? So what I mean is, can they be applied on a code that is not designed for the tools, or can they be applied by a non-expert person? So the goal of this ongoing work and my PhD is to review some of these tools in order to define verification process and answer this question. This process will then be applied to my study case, which is Paparazzi, a drone autopilot. So today I will present my first result. It's an analysis of a mathematical library of Paparazzi. So we use Fmacs4 in order to verify that there are no runtime errors in the code, and also verify some functional property. And the goal was just to apply Fmacs4 on the existing code without having to modify the code. So let's start by presenting Pharmacy. So Pharmacy is a C-code analysis tool developed by CEA and INRIA. It had the advantages to be modular. So it supports different plugins that implement several formal methods. The general process to verify a C program using Pharmacy is first to specify the property you want to verify. So to do this, you use Axel, the specification language of Pharmacy. So with this language, you can define contracts, precondition and postcondition, assertion in the code, and also you can annotate loop with variant and invariant. Then Pharmacy will generate an abstract syntax tree that represents the code with the annotation. This tree is then sent to some plugin. We have plugins that can add other annotation to verify some new property. And of course, you have some plugin that will analyze this tree in order to verify if the property are correct or not. So this tree is the common part of all the plugins, and it can be shared between the plugins, so we can associate several plugins, so several formal methods for the same verification of the same code. So here's some example of plugins that I used during this work. So we have RT for runtime error that add annotation in the code that correspond to potential runtime errors. Then we have WP for weakest precondition. So it implement weakest precondition calculus. And this plugin is interfaced with Y-tree. So we have access to automatic prover in order to automate the verification of the property. Then we have EVA for evolve value analysis. So it's a plugin based on static analysis by abstract interpretation. And it had the advantages to compute accurate interval of potential value for each variable in the program. Now let's present Paparazzi, the study case. So Paparazzi is an autopilot developed at ENAC, and it's open source. It's a complete drone control system. It offers the control software part and some design of hardware components, and support drone and aerial vehicles. So the library we use today is Paparazzi Algebra, a mathematical algebra library coded in C that represents almost 4,000 lines of code. In this library, you can find some representation of vector, different representation of vector rotation, elementary operation on this representation, and then conversion function between these representation. So the main part of the verification is to ensure that the conversion function, the result, is equally represent the same rotation as the input. And all these functions has several versions, version that use fixed point representation with int type, and also floating point version with float and double C type. So now let's start the verification part with the absence of runtime errors. So there are several types of runtime error, and we want to verify that these errors not occur during the execution. So the goal here is to determine the minimum contract, so the minimum precondition, in order to ensure that during the execution, there are no runtime errors. So the process we use is to launch the analysis of Pharmacy on the code using RTE plugin that will add annotation corresponding to this potential error, and WP that will try to verify this assertion. And by analyzing the assertion that are not proved, we can deduce the missing information in the contracts. So here is a simple example to illustrate the verification process. So if we want to analyze this line of code, so x of c takes x of a times x of b, where a, b, c are pointer on structure that contain at least an integer element called x. If we launch the analysis of Pharmacy with the RTE plugin, we find two potential errors. So first, the pointer might be not valid. So here is a screen capture of the Pharmacy graphical interface. So the blue part is a Axel annotation. Here is an assertion. RT and memaccess are just labeled, and the valid is the predicate. So the address x of c is the predicate, verify that is if x of c is valid. The yellow dot means that this predicate has not been verified. So all the pointers, we don't know if they're valid or not. So to ensure that, we have to require in the contract as precondition that the pointer might be valid. Because if we get invalid pointer in the function, we cannot deduce any information. The second error is that the value might be not bounded. So the product might produce an overflow. So we have to determine, analyze the code in order to compute interval for x of a and x of b that will ensure and guarantee that there are no overflow. And this was the main part of the verification of absence of runtime error, to deduce the interval for each variable that will ensure that there are no overflow. So when we deduce this information and define the contract, we launch EVA and WP to verify this contract, and we have to associate both plugins. Because when we compute the absence of overflow, and we use a lot of pointers pass in parameter, WP was overloaded because it hasn't an alias analysis, and so it loses information about the bound of the input. But if EVA has not this problem, it can compute accurate interval of potential value for each variable. So it can verify that there are no overflow, but it cannot verify that the variant and the invariant. This was the same problem raised by Vasil Todorov in this thesis, and he has to associate WP with Astray, another static analysis tool. So the verification of overflow has mainly done and only done on the integer path, so fixed point representation. For the arithmetic model, we use a real model. So it's a model provided by Fmics4, and we represent the numerical value by a real number in a mathematical sense. So using this model, we can verify that there are no division by zero, the lack of derivance of invalid pointer. But as we represent number as real, there are no overflow because the value are not bounded. And using this model, it was easier to verify the property, the runtime error. Now let's talk about the functional verification. So the goal here is to offer some guarantee on the behavior or the result of a function. So for example, if we want to analyze and provide some behavior or guarantee on the result of the square root function that take a float as input, that is positive, we might want to verify that the result is also positive, but also if we square the result, then we get the initial value. That is potential functional property we want to verify. But if we use C semantic and we compute square root of 2, so float can represent finite value, but square root of 2 is an infinite digit value. So we cannot represent exactly square root of 2. And so we cannot verify this property. But using the real model, we can expect to verify this property. So we can, with real model, we can verify some mathematical property. So it's why we use this model is mainly for verify some functional property. And the functional verification takes more time, so we had to focus on some floating point function. So how do we specify the functional property? So we use the Axel logic in order to express the functional property, represent the mathematical result we want to verify. So first we have to define types that represent vector, matrix, quaternion, also elementary function that operate on this type, and then the conversion function, so the main part we want to verify in this library. So for example, we define RMAT of quat is a function that takes a quaternion and return a rotation matrix. So the definition of this mathematical function, we base the expression on some scientific results that will verify the formula by hand. But as we want to verify some functional property with formal method, we cannot base our verification only on result verified by hand. So we define lemmas. So lemmas are the goal is to verify that the mathematical definition are correct. And these lemmas are then automatically verified using the SMT solver, using WP. So we have strong guarantee that our definitions are correct. So for example, if we want to verify that the conversion function produces the same rotation, mathematically, we can define that for all quaternion and all vector, the rotated vector computed by the quaternion is equal to the rotated vector produced by the rotation matrix that have been computed using the RMAT of quat function. And then when we have all this theory, we can define some predicate that represent the mathematical, the functional property we want to verify. So for example, M is a rotation matrix. We compute M and its time its transpose and verify that is equal to identity. So we faced some problem during this functional verification. We had some function that use trigonometric function from the Leipzig, but this function does not provide any mathematical information. So we have to extend the contract and adding the last line, for example, for this sinus float function. So we add that the result is equal to the sinus defined in Axel. So using that, we can have some mathematical results in the function. So it's complementary with the use of real models. So we can verify mathematical property in the code. And also some lemma could not be proved using SMT solver. So we had to enable the interactive mode of pharmacy. So we use Coq to manually verify some lemmas, some property that the SMT could not prove alone. So a little summary about the functional verification. So using functional verification, we can offer some guarantee on the behavior of the function. So the functional property are expressed using the Axel logic language. And the verification can be done automatically or interactive. And we use the use of the real model. So we offer no functional guarantee during the execution because we do not represent exactly the C semantics. But we can use it to verify that the code is correct in a mathematical sense. So we verify that mathematical property are respected. So a little conclusion. So we verified the absence of runtime error in the library. We verify some functional property on some floating point function. And this verification represents approximately 3,500 lines of annotation. All this code is available on GitLab. And some perspective, we want to finish some remaining code proof. All the lemmas are not proved yet. We want to verify that when the function are called, the caller respects the contract we define. So we verify that there are no runtime error and the functional property. We also want to verify the floating point library without the real model. And then another perspective that is different than the verification of the library, mathematical library, is to verify the Papardi flight plan generator. So thank you for your attention and watching this presentation. If you have any question, you can send me a message or ask me the question during the conference. I will answer it. So thank you.
Thank you very much, Baptiste. So there are already 2 questions in the Q&A that you can answer. One from Bob, one from Natasha.
Yeah. So can pharmacy plugins interact and or reuse intermediate results? So yes, it's why we use and associate EVA and WP, because EVA provides some information about the interval of possible value for each variable. So we use this information to prove some information about the bound for to avoid some overflow. And WP can verify other property like the loop invariant. So the information or interact, both plugins interact with each other. So second question, which version of pharmacy did you use? I used the last one, so the 23. Yes. So last question, you mentioned it might be needed to set bound on value of argument of math function. It is realistic. I have feeling engineers don't really consider the values they pass into mathematical function. So if they get an error that say this parameter must be less than 100, that might be confusing. So yes, it's one of the problem, and it's one of the perspective of the future work, is we provide some bound for the function in the library, but we are not verified that when the function are called, if the caller respect the precondition, and for the future engineer that will use the function, yes, it might be a problem. So we have not studied this part yet. Which lemmas were hard to prove in pharmacy and require Coq? So one of the lemmas that I show that for the equivalence of the rotation matrix and for the function that convert a quaternion into a rotation matrix that is equivalent than a quaternion function. The lemma is not complicated to resolve by hand. It's a lot of factorization and some simple trigonometric result, but solver are not able to factorize in the right way the formula. So by hand, we can help and move the equation to be simpler. So yes, it's especially for this type of equation.
Okay, so I hope Bob is satisfied with the answers. If not, Bob,
yeah,
say something in the chat. Yeah, he's happy. there is one question from the chat from David also. So
okay. Call the verification of runtime error hamper code reader LP, since for each variable assertion are generated in the code.
I'm not sure, David, since you're on the panel, maybe you can.
Yeah,
just...
sorry, I write in the chat because for the panelists, I can know you to use Q&A. So I was just thinking,
right.
Yeah, find a bug in Zoom. At least I could not write. I don't know if I missed something. I was just thinking, since it appeared to me that these assertions were inserted in the code, right? Yes, these contracts you are using.
The assertion are added by RT plugin. So they are added during the verification. So not exactly in the code. So they are displayed in pharmacy graphical interface. But what I had of annotation is just contract in at the beginning of the function. So we have precondition, postcondition. So it add information for in the code. So it's important and give information. But all the assertion are just added during the verification. So it does not affect the readability of the code.
Okay, understood. Thanks.
Thank you. I have maybe one more question. Okay, yeah, no, there's a comment from Morris. Robert is commenting, I think, on the same question, so it's worth it. So he says, if I may make an outsider comment, for some problematic programs, these assertions annotations can seriously hamper readability, but then these are really complicated programs, which are also kind of pathological examples. So I guess he concurs with the assessment that it only hampers the readability in very corner cases.
Yeah.
And to speak of corner cases, I was going to kind of make a reference to the invited talk Joe gave yesterday with respect to evidence-based assurance. So is there any way you think you could be able to pinpoint some corner cases during your analysis where you could produce an execution trace, just a function call, a context for a function call, where would you say, look, it could have gone wrong here, but it computes correctly, and thereby provide additional assurance to people that beyond just proving in pharmacy that the computations are correct, you can actually show that it's, yeah, look, it does look correct also. Do you think that would be possible?
A corner case, I think I have an example of a problem. I don't know if it answers your question, but they use a lot of shift and in left and right for division. But in pharmacy, we have some corner case or with the division where they are negative, you can produce false result, but they don't think about this kind of property. And this autopilot it exists from 10 or 20 years and you have no problem. But with pharmacy, it shows some error for the shift.
Mm-hmm. So there is not a place where you can, like, while running a proof, you could say, well, here actually the proof is complicated, so maybe we could generate a test for this kind of test to test this kind of case.
Yeah. No, actually, I don't have example.
Okay, sure. Because this could be interesting, but it's obviously not trivial at all.
Yeah.
There's one more question. I think we have time to pick up this question. It's from Natasha.
Yeah. What was the time needed to perform the analysis with Fmics4 approximately, and timeout was set to what? So I have during the verification, so it takes me 4 months, I think, to do all the analysis. And I was a beginner, so I have to learn pharmacy, and I done something that might be not, I will not do now because it's not efficient. And at a certain time during the verification, I had to use a timeout that or 30 seconds. But now I use some different model for representing the memory, and they're set at the default value. It's 10 seconds. And to verify all the library without the cache, it takes approximately 10 minutes of verification on my computer.
Okay. Can you give a rough estimate? Like, okay, so you said 4 months.
Yeah.
How much of that time did you spend learning the tool? How much did you spend preparing the model, and how much? So you already said how much you spent actually running the verification, but yeah.
I think 1 month to learn, but during all the 4 months, not every day, but during the verification, I learned new things that help and facilitate the verification. So even at the end, I discover new features that help, and is one of the problem I had with pharmacy, that there are a lot of features that you don't understand, we discover lately that can help, and that might be very specific for specific case. And you have, in the best case, you have to reread all the documentation, but when it's very complicated to understand what the good option will be for a future case.
Okay. Okay, thank you very much, Baptiste.
Thank you for the question.
Very nice talk. So we can move to the last talk by Davide. I don't know if Davide will be able to ask questions to himself in the chat. We'll see.
I do this every day. It's possible.
In the chat.
Yeah.
Okay, go ahead.
So the title of the presentation is Formal Analysis of the Unisig Safety Application Intermediate Sublayer. I am Davide Basile. This is a joint work with Alessandro Fantecchi and Irene Rosadi from ISTISENAR Pisa, University of Florence. So we start with the background on the Horizon 2020 Shift2Rail initiative. Shift2Rail is a joint venture between European Union and railway European stakeholders for pursuing research and innovation activities in the railway domain. Formal methods and standard interfaces have been identified by Shift2Rail as two key concepts to enable reducing the time it takes to develop and deliver railway signaling systems. It will reduce the costs for procurement, development, and maintenance. Indeed, with standard interfaces, it is possible to have a system of systems that are interoperable between each other. This means that different subsystems can be provided by different providers, so reduce the costs. However, for doing this, it is necessary that the specifications of these interfaces are rigorous and are verifiable. For this, formal methods help. However, there is still an obstacle to the widespread adoption of formal methods in the railway industry. Mainly, there is an absence of clear idea of the benefits from the adoption of formal methods, and there are no clear guidelines on how to use them in a cost-effective way. For this purpose, there is a ForSecurail project financed by Shift2Rail that has a workstream, the first workstream, that is investigating the benefits of formal methods for specifying standard interfaces. There are several work packages for selecting firstly a suitable case study, that is in this case an industrial railway standard interfaces, and then there is a work package on developing a demonstrator of formal methods to be exercised on the selected case study, and finally to perform a cost and benefits analysis of the adoption of formal methods in the railway environment. In this paper, we contribute to this workstream by applying a specific formal method to the selected standard interface case study of the ForSecurail project, and we derive costs in terms of man hours and benefits in terms of issues that have been found in the specification. These issues have been validated by the partners of the ForSecurail project. The formal method that has been used is statistical model checking and UPAL. The idea of statistical model checking is to run in a control number of simulations that are probabilistically distributed, so it's a Monte Carlo simulation. The simulation is performed on a model of the system, and in this way it is possible to obtain a statistical evaluation P prime of some formula phi, and that comes with some guarantees on the error bound and the confidence interval. In particular, the probability of phi to hold lies within the interval defined by epsilon, with the probability greater than 1 minus alpha. One key concept is that the number of simulations n only depends on these parameters alpha and epsilon, and is independent from the size of the model. So the pros of the approach is to avoid full state space exploration. Moreover, statistical model checking is easy to implement. One only has to implement a simulator, and it is possible to put these simulations in parallel to make them more scalable. So on the converse, we have no exact results, of course, and moreover, with the statistical model checking, it's difficult to catch those rare events that are events that occur with a very low probability. The tool that has been used is UPAL. UPAL is a widely used tool for specifying and analyzing railway systems. The model are networks of stochastic price-timed automata, and UPAL, of course, implements statistical model checking. Moreover, UPAL offers graphical interactive simulations with the animations of the various steps of the execution, and this is really helpful to interact with the stakeholders, and of course, model checking. The case study is the UNISIG RBC handover. So UNISIG is an industrial consortium that is that has the goal to create and develop the signaling European technical specifications that are the RTMS and the TCS. Fmics4 is an associated partner of UNISIG and is involved in the first workstream of the ForSecurail project. So each RBC, an RBC is a component of the signaling system and is in charge, it's a radio block center, it is in charge of managing an area, supervising an area, by communicating with the trains. When a train approaches the border, there is an exchange of information, an handover of the train from one RBC to the others. There are UNISIG subsets that specify how this handover protocol happens, and it is a layered structure protocol. So in particular, there are several subsets related to the various layers. We focus on the subset 98 that is the safe communication interface, is a subset of 2012. It is composed of two sublayers that are the Safe Application Intermediate sublayer, SAI, and the Euroradio safety layer. Then there is an application layer that defines the application messages exchanged by the two radio block centers and the other low-level layers. The Safe Functional Module is in charge of implementing the safety techniques. In particular, we will focus on the Safe Application Intermediate layer, and we will model all the requirements of this sublayer. So the function of the subset 98 is to specify the protection from threats for open transmission systems that have been identified by the CENELEC standard 50159. In particular, the SAI sublayer implements two specific mechanisms that are the sequence number and the triple timestamp. The sequence number protects from the threats of repetition, deletion, and resequencing. These are threats where a message is either repeated, is deleted from the stream, or two messages are swapped, so they are resequenced. The protection adds a sequence number to each packet, to each message. In this way, it is possible to reconstruct the order in which this message has been sent. Concerning the delays to each message, a triple timestamp is used. There are three timestamps that are used to compute the offset between the clocks of the two radio block centers. Once this offset is computed, it is possible to reconstruct the delay in sending a message to check if the delay is excessive or not. The other threats are masquerade, corruption, and insertion, and these are dealt by the Euroradio safety layer that is not addressed in our model, and are the protection use cryptographic primitives. So we now move to describe the formal model structure. The two entities are specular, so for a matter of space, we just show one of the two devices, could be the initiator of the responder. The main module is the SAI module, that is again divided into sub-modules. Each of these sub-modules is a template automaton in UPAL. These modules exactly model the specification given in the subset. Of course, to have a closed loop system, to perform formal verification, we also need to have a user of the SAI module. In this case, this user is in charge of opening the connection and sending application messages. And on the other side, we have the environment that is in charge of sending the messages. Each communication happening inside a computer, inside the radio block center, is asynchronous. These are channel synchronization. However, the communication happening between two remote devices, two remote radio block centers, are asynchronous. In this case, we use a signal queue of messages that are global variables. In particular, each message that is sent to the other device is included in the queue of messages. These asynchronous messages are stochastically delayed, and there is a fault injector that is another component that inject faults on the stream of messages to simulate the threats happening. This could also be a model of an external attacker artificially injecting faults in the model. We now directly briefly show the UPAL tool with the model that we have developed for this paper. So the subset identifies signals, and each signal is paired with a constant, a unique identifier that is used to identify that specific signal. Then in the model, and these are the global declarations, we have various parameters. This is a setup of the parameters for the experiments. One important thing to say, for example, is the structure of each signal. So each signal is rendered as a structure in UPAL. In this struct, the components, the fields of this structure are taken from the subset. Each message has a unique identifier. These are the timestamps used to implement the protection from the delay. This is the sequence number. Then there are the user data, and each data comes with the offset for the delay. These are the broadcast channels that are used to implement the communications. The communications, each channel is actually an array of n channels. In this case, n is the number of operating devices. In our experiments, we have 2 radio block centers. And then we have the queue of messages is rendered as a 2-dimensional array. And there are other constants and the various global functions that are used by both the various automaton. We can briefly show the user automaton. This is in charge of opening the connection and sending periodically messages to the SI to perform the experiments. And this also handles the disconnection. This is the user of our model. And then we have the model of the user or the tester, if you want. Then we have a model of the environment. So starting from the Euroradio sublayer, this automaton is in charge of enqueuing and dequeuing the messages in the queue of messages. We have one for each of the entity, for each entity in the experiment. In this case, we have 2 radio block centers. The messages are enqueued with no delay. We have functions for enqueuing messages and dequeuing messages. Instead, the delay happens on the side of the reception. So there is an exponential rate modeling the delays in which the messages are received by the partner. And you see that depending on the specific ID, we convert each message to be that is received into a message that is then sent to the other component. Then there are a set of templates that are the templates. So so there is also, the fault injector. So there is a fault injector model is the one that is injecting the channel faults into the system. We have here a probabilistic choice where each threat happens in a specific probability weight, and to each threat is associated a function that is implementing the specific function. For example, deleting a message from the queue and so on. So we can model the probability, the likelihood of these threats to happen, and also the period in which these threats happens, using this exponential rate again. So what I have showed until now, these are all the models that are used for having a closed loop system, that are the models of the environment and the models of the user. The actual software model that we want to specify here is instead composed by the other templates of the SI component. Here I may only describe the component that is the template of the SI receiver. This is the piece of the SI module that is in charge of receiving a message from the Euroradio and then checking if the packets have the correct sequence number and delay time. If this is not the case, an error is triggered. So for example, when a message is received, there is this state connected, the state check data message that is a committed state. These are used for implementing atomic operations with various transitions. So various transitions implementing an atomic operation. For example, if the sequence number is negative, then the message is discarded. Otherwise, an error is, otherwise if the message, the sequence number difference is 1, the message is correct. If this is not the case, an error is triggered, and then depending on a tolerance parameter, there could be either a disconnection or there could be that the operations continue to run once the error message has been communicated. So this was a quick overview of the model. Now to the formal verification phase, we have inflated the probability of fault injection. In this way, we avoid rare events. And other failures from lower levels have a lower probability of occur. For example, the disruptive connection from the communication layer. We used a schematic verification methodology where we measure the probability that the system does not behave as expected in the presence of a threat. Of course, this measure only makes sense if the probability of the threat to occur is not close to 0. For example, here we have a property that is measuring the probability in 1000 time units that we reach a bad configuration where we have a difference between the last two sequence number that is negative, and however, even if it is the case, we have reached one of the states of error or correct validation of the message. We know that this should not occur. We want this probability of reaching this bad configuration to be close to 0. But this value close to 0 only makes sense if we are in presence of the threat. In this case, we also have to measure in the same setup of parameters that the probability of the threats to occur. In this case, we have a sequence number difference between the last two received sequence numbers that is negative, that must be non-negligible. Of course, to obtain this value, we need to inject the corresponding faults of resequencing and so on. So coming to the benefits, this is a table summarizing the errors that have and the issues that have been found in the subset. We emphasize that this subset has been around for 10 years now, and it's already in operation. However, applying formal methods, we were able to discover issues that have been validated with the industrial partners, and this will lead to new versions of the subset. Actually, there are requests for changes that are being made to fix some of these problems. Mainly, all these problems are related to specific configurations that are reached, and where the subset does not specify what operation has to be performed in this specific scenario. For example, the clock offset update procedure is used to update the clock offset periodically. During this procedure, if a specific check that is performed on the timestamps is not successful, the subset does not specify what operation must occur, if the connection have to be closed and so on. And this is just one of the examples of all the issues that we have found. Coming from the point of view of the cost, we have measured the costs in terms of credits that have been sustained by the third authors to learn the formal methods and to apply them to this specific case study. The learning cost I've measured as the credits that have been taken by the third authors to give the software dependability university course at the University of Florence. At the University of Florence, this course was given by one of the authors of this paper, and this amount to more or less 160 hours that are the 7 CFU, university credits. And from the analysis, the credits have been, the hours have been evaluated using the credits of the master thesis that has been sustained by the third author to develop the model and the analysis that has been described in this paper with the supervision of the first two authors of this paper. It must be noted that there is no clear distinction between the phases of modeling and verifying when concerning the work effort in hours for the analysis. Indeed, from the first prototypes of this model, there was a continuous verification and simulation phase to check at each step that the changes that were made to the model were correct. And this is the correct way to proceed when developing a system. So there is no clear distinction between these two phases. Of course, the data concerning the credits, the university credits, and the hours are available online, consulting the regulations of the University of Florence, and the links are in the paper, in the references. So concluding, we have applied formal methods, and in particular UPAL statistical model checkers, to an industrial railway standard specification from 2012. We have measured roughly the effort in terms of credits that have been sustained by the third author for a master thesis supervised by the first two authors. So we have a rough measure of the number of hours that are needed for learning formal methods and applying them. And from the point of view of the benefits, we have identified several issues that were due to a specified scenario. And these issues have been confirmed by the industrial partners of Fmics4, and this will lead to new requests for change in the subset. Concerning, there are other benefits that we put as future work here. Indeed, the model is publicly available, and the link is in the paper. And from this state machine model, it is possible to start other activities of implementation, for example, model-based testing or model-based software development. It suffices to take the software model, so not the environment and the user model, and translate them, for example, into UML notation to generate code directly started from this model. So there are other benefits other than the issues that have been identified with this particular activity. So this concludes the presentation, and thanks for your attention.
Thank you very much, Davide.
Thanks.
Alessandro? Nice work. Also nice to have this kind of interactions with the industry ongoing. It has been done for a while, but it's important to keep it up, I think. So there was one question which is already answered in the Q&A about the version of the tool.
Yeah, I can add on this that is the version 4.1.24 of November 2019.
Okay.
To be more specific.
Yeah. So while the attendees are thinking, or panelists are thinking of other questions that can pop up in their minds, I have a couple of questions. So the first one you mentioned, so you went quickly through the benefits slide, but the impression I got is that you have two kinds of problems by the moment of their detection. So there are problems that you've detected during the preparation of the model and problems that you have detected during the verification. And so two sub-questions. So one sub-question, how easy was it to resolve the under specification that you have detected during the preparation of the model? And the second sub-question is, did you detect any inconsistencies? Because this is also part which sometimes comes up when you have to actually update the spec, because when you prepare the model or verify it, you realize that it's the spec which is incorrect.
Okay, so let's say our goal was to discover issues. Then let's say to implement a new solution is another problem, because we needed to check that our solution was okay with the domain experts. And this was, let's say, a problem that we did not face. So what we did was to go for the simplest possible working solution. It's maybe not the best one. For example, concerning the sequence numbers, there is 4 bytes that I've used, but the specs never mention what happens at the 0 crossing. So when the sequence number goes from 60,000 to 0, the simplest solution that we did was to close the connection when we reach the maximum. Of course, we don't think this is realistic, but for the purpose of the current specification, it was okay. Let's say the elicitation of requirements, of new requirements, is another problem. Mm-hmm. And we don't know if our solution is in conflict. We don't think so, because the verification was correct, but more complex solutions could open new problems.
You didn't get any feedback about this solutions from your partners?
Yeah, we know that one solution is not what is in the request for change, because it's not realistic. We know that we found the problem. Finding the solution would have required elicitation, an elicitation phase, and so on.
Okay. Right.
It's very difficult to guess the right solutions because there are so many possible. We went for the easiest one to continue, because otherwise we would have stopped.
Okay, and I guess you didn't find any inconsistencies, like contradictory, did you?
Yeah, we didn't. Let's say we had to perform, of course, a verification that our model was correct. So there was no deadlock, no loss of messages, no overflow of the buffer of messages. This was verifications of things that were not in the specifications. Then the real requirements was that the protection was effective. There were no cases in which, for example, there was an error in a message and the message was deemed okay, or vice versa. No false positive and no false negatives. So we verified this. But as I was describing, mainly these issues were rare scenarios that brought the system to a configuration where it was not clear what to do. And this was the problem hampering the interoperability of devices developed by different partners.
Okay, great.
In fact,
there's a question. Oh, yeah, sorry.
If I can add to this reply, actually, in the interaction with the industry, we understood that different providers implementing the same specification have used different interpretation, different solutions for some of the issues that we have found. And this, in some cases, brought an actual not interoperability of two RBC to radio block centers provided by two different providers. We know that there is at least one case, an actual case of this, for which an interface computer has been introduced between two RBC in order to solve any issues.
Right. Okay.
So this is, but anyway, it appears also that the specification does not want to give too many details because these are perceived as limiting freedom of the implementers.
Yes. Yeah. This is a classical. It's actually a restriction which is often imposed on themselves by the kind of leading partner of the project to leave enough leeway for the implementers to be creative. But I think what you're saying is indeed very important, because verifying that so this is some kind of integration test to see that at the end solutions provided by different subcontractors do actually work together well. Yes. Okay, I think we have time to pick up the last question from Bob.
Yes, there is a question in the Q&A.
Yep.
Yeah, the question is it possible that mistakes have been made when constructing the UPAL models? Are there strategies to prevent this from happening? So the answer is yes. When we were modeling, actually the student was modeling the system. We were supervising the student. She made some error. And that's why there was, as I was saying in the presentation, continuous simulations and verifications. And for example, at some point we needed to introduce invariants in each state to be sure that each channel synchronization was not lost, because UPAL statistical model checker only works with broadcast channels. So the semantics of broadcast channels is that the message is sent, but it is non-blocking. I mean, it could be lost. If the message is received, is okay. Otherwise, it's discarded and the system continues. And we did not want to have this scenario of the message being discarded. So we had to check with invariants. So we had to do some extra real model checking to check that the model was correct. And also at the end of the day, even if we see all these models and verification as a black box, the starting point was this set of requirements. At the end, we had these issues, and we came back to the railway engineers with this set of issues, and they confirmed that some of them were really there. So this is also a sort of validation of the work that has been done.
Okay, thank you very much. So I think now it's time. Mix of using. Okay, so a mix of using the model practically, using multiple techniques, and human in the loop. Interesting. Thank you. Message from Bob. Good. Thank you very much. Thank you. Big thanks to all the speakers of this session. I think now it's time to let the people take their breaks. So see you around. Bye-bye.
Bye. Thanks.
Bye.